All right, hello class. Okay, so I'm going to talk about thermal equilibrium today. And let's say we have two objects, A and B, that are in thermal contact with each other. And let's say temperature of A is greater than the temperature of B. And so heat is going to flow spontaneously from A to B, from hot to cold. So heat is going to be leaving the substance A, which will cause the temperature of A to decrease, and heat enters B, which causes B to increase. And again, this exchange is only happening because these are at different temperatures. So if you look at it, like A is hotter and B is colder, but as this heat is exchanging, temperature of A is falling, temperature of B is rising, eventually they're going to be at the same temperature, and then this exchange will stop. And then they'll just remain at that temperature, whatever it is, like wherever they meet up. And we call that the equilibrium temperature. So we put these two objects together, and eventually, if we have let's say that A and B is our system, let's say A and B is an isolated system, which means, here we have this boundary, and say nothing enters or leaves, including energy. Now, this would probably not typically be the case. Like, say you have, as an example, say you have a glass of water, or just some drink overall, and you want to, you want your drink to be cold, so you drop an ice cube in it. Or multiple ice cubes, but you drop ice into this cup of liquid. Let's just say water. And so, like, the ice could be A, liquid B, so energy is going to flow into B, from the water into the ice, until they reach some common temperature. However, there's also the room. Like if you just have a glass of water here, you pour ice into it, the room is at a different temperature. The room is just at room temperature. Maybe it was the same as the water was initially. But once you put ice in the water, and energy is going to flow from the water into the ice, so that's going to lower the temperature of the water, but the water is in thermal contact with the air, so energy is going to be flowing in from the room. So this is not, just like the water and ice are not an isolated system here. There's also the room to consider, just the overall environment. Now we can maybe fix that by putting this in an isolated container like a thermos. However, the thermos itself is in contact with the liquid, so that's part of the system as well. So basically, we just have to be careful. We're going to talk about energy flowing between like the different parts of the system and reaching equilibrium, at some final temperature where everything is the same temperature. And we just have to make sure that all that energy is accounted for. So we're not like energy, like if we just had this ice and water mixture and didn't consider the room, well, that'd be a problem because we do have energy entering from outside. So we'd have to consider the room itself as part of our system for what we're going to do, like if we want to find this equilibrium temperature. And so we just have to be clear that our system is big enough that there's no energy exchange with anything outside of that. And so the basic idea behind finding the equilibrium, I think it's best to look at this in terms of an example. So I've got one in the notes. Actually, maybe I should make up a problem that's a little easier to start with. Yeah, I think I'm going to start with a kind of a simpler example of equilibrium. Okay, now I like to draw things in different ways depending on the state of matter. So like the way I do it, I draw like this would be a solid. Now I draw a liquid like this, and a gas like this with dash lines. I don't know if I read that somewhere or just made it up, but that's how I do things. You obviously don't have to do this. But I like to kind of draw what's going on when we mix things together. And so I draw solids, liquids, and gases differently. I think it's important to keep these things in mind when you're doing these problems. So I'm going to start with a simple problem. Let's say we have water. So we're going to have two types of water. So let me write this down. Let's say we have A and B. And this is among the simplest kind of equilibrium problems that we could come across. So let's say system A, we have a mass of, say, 500 grams, and an initial temperature, I'll just say TA, of 25 degrees Celsius. That's around room temperature. So you have 500 grams of water at roughly room temperature, say 25 degrees Celsius. And then B is also water. We'll say the mass of B, let's say it's 200 grams. And the temperature of B is 90 degrees Celsius. So this is like nearly boiling water. It's much hotter. And so you just mix them together. So you've got, like, say, a cup of water with A, and you pour this 200 grams of much hotter water. Now, again, there is this issue of the environment, which could either be the air in the room or the container that's holding that, because energy can flow into or out of the container. And what we're going to do is just ignore that. We're going to say our system is A and B, and say that no energy is going to escape into the environment. So again, this is not the most realistic example. Now we could make it realistic by having a container, but again, I want to keep things really simple for now. So we're going to say that this A and B is isolated system. Okay, now for an isolated system, we can write down this equation. I'm just going to write this down. Sigma Q equals 0. For sigma, that just means sum. So there's going to be heat flowing around in our system, but since nothing is escaping or entering from outside, we can say that the total heat in our system remains unchanged. So this is where I really like to draw pictures of what's happening here. So actually I'm going to move this down a little bit. So again, we're starting with something a little bit unrealistic, but very manageable. So A is in a liquid state at 25 degrees Celsius. B is in a liquid state at 90 degrees Celsius. I'm also going to write down our basic equations. So remember, for phase changes, Q is mL. For temperature changes, Q is Cm delta T. We're not going to need the first one right now, so let's ignore that. Okay, so we mix these two things. And obviously what's going to happen is heat is going to flow from B to A. So A is going to warm up, T is going to cool down, but they're going to meet at some equilibrium temperature. And we know that this temperature they're going to meet at, here we'll call that TE for equilibrium. So they're both going to meet at this common equilibrium temperature. We know it's got to be somewhere between 25 and 90. And so we know that these things are going to remain in their liquid state. And so I'm going to call this Q1 and this Q2. So Q1 is the heat just for this change in temperature. So we're going to use this equation, Cm delta T. And I think I'm just going to write it down. And there's something we have to be a little careful about. But basically, because these exchanges are happening within the system, like what is Q1? That's the energy that's added to A while it's coming from B. And so basically, we can say that Q1, this equation here, we have Q1 plus Q2 equals 0. Now, the thing we have to be careful about is in order for these to add up to 0, if one's positive, the other has to be negative. Remember our convention, if heat flows into a substance, Q is positive. So we should expect Q1 to be positive because heat's flowing from the hotter substance into the colder substance. And so A is gaining heat, so Q1 is positive. B is losing heat. It's losing energy. Heat is flowing out, and so Q2 is going to be negative. But again, all the heat that's flowing from substance B is going into substance A, according to our assumption, which maybe isn't the most realistic in the world. And the good thing is that that's going to be taken care of automatically in this equation. So remember, the equilibrium temperature, we don't know what it's going to be, but it's going to be between 25 and 90. So if we look at delta T for here, like just on top, delta T is going to be, it's a change in temperature. So we've got a final value minus its initial value, which was 25. So that's greater than 0. Down here, delta T is going to be the equilibrium value minus 90. And we know that this value is going to be less than 90. So that's going to be less than 0. So again, we don't have to really worry about it. It's going to come out naturally if we just plug everything into this equation. So let's do that. Q1 is going to be C. Maybe we'll call this QA plus, let's stick to Q1 and Q2. So again, Q1 is this process here, where we're going a temperature change. So this would be the mass of A, and delta T, that's always final minus initial. Now I'm kind of running out of room. This is 25 degrees Celsius, but I'm running out of room, so I'll just leave that off. And then for C2, we have CMB times TE minus 90, and that equals 0. So just write that with a little more room. Okay, so that's our equation. Now one thing, I just wrote Cm delta T. I didn't write CAMA, and then that's delta T, because both of these are water that are always going to be in a liquid state. So we just have, they have the same specific heat, and they're both in a liquid state, so we don't have to worry about whether or not it's ice or a liquid. So, yeah, we can just write C. Now it's interesting, we can just get rid of C entirely because the right side is 0. So if we divide everything by C, that'll be gone. But sometimes you'll have like C, you can have different values of C. Because, well, if you have two different materials, like if this was water and this was alcohol, they'd have different C values. So sometimes you'll have to be more clear what C you're talking about. But in this case, that's not going to be an issue. And so our goal is just to solve for TE And again, that should be fairly easy to do. So again, let's just cross off these C's. Just we have limited board space here. So let's just distribute things. We have MA TE minus MA times 25. And again, that's degrees Celsius. But I'm kind of have limited room here. So here we have plus MBTE minus 90 MB equals 0. So let's collect everything on one side. Well, let's collect everything with TE on one side and move everything else to the other side. So here we have these two terms. We can say TE times MA plus MB. And then these terms we put to the other side. So we'd have 25 MA plus 90 MB. And remember, each of these numbers, these are like Celsius degrees. Maybe I'll put that back now that I have room for it. Yeah, I hate neglecting units, but kind of forced to in this case, at least as far as writing them down. Okay, and now it's just a matter of solving. So what I want to do, I can put these equations somewhere else. Let's look at these pieces. Let's look at 25 MA. So 25 times 500. We're probably going to want to convert. No, we don't need to convert. Never mind. 25 times 500. 25 times 5 is 125. And that would be grams times Celsius degrees. So that's this part. Now 90 times MB. So 90 times 200, well 9 times 2 is 18. And then, wait, let's see, we had 90, yeah. So that'd be 18,000. And again, grams times Celsius degrees. So, yeah. Okay. And so our equilibrium temperature, on the right side, we just add those up. So 18,000 and 12,000, that's 30,000. So we have 30,500 grams times degrees Celsius. And then we have to divide by MA plus MB, which is 700 grams. So again, I mentioned earlier, we probably want to convert to kilograms. No, we don't need to because we got rid of this specific heat. Specific heats are usually in like kilograms, like joules per kilogram Celsius degree. So if we had different materials, we'd have to convert to kilograms, most likely. But here, we didn't need to do that. So the grams cancel out. So 30,500 divided by 700, what's that? 30.5 divided by 7. So let's see. So it's going to be around 4.36. I definitely did something. This should have been 305, not 30.5. So 43.6, which, again, okay, so we have a number. The equilibrium temperature is 43.6 degrees Celsius. So again, we have a number. And now the question is, Well, we wanted to find this number. We found it, so we're done. Now, really, we want to see if it makes sense. Like, I initially got an answer of 4.36, which makes no sense at all. That'd be like you have water at room temperature, you pour almost boiling water in, and then it gets colder. Obviously, that makes no sense. But again, I made a simple decimal point, just in the wrong place kind of thing. But yeah, it should be 43.6, which is between 25 and 90. Equilibrium is going to be somewhere in the middle. And it's a little closer to this one, but that makes sense because there's a lot more of system A, more than twice as much. So it makes sense that the answer is closer to A than B. So overall, yeah, reasonably happy with this number. And this is basically the procedure for all these equilibrium kind of problems. It's just they can get more complicated in the details. So I want to go to a more complicated example now. So I'm going to erase all of this. And again, these problems take up a lot of space. That's going to be a little bit difficult just to fit it on the board. So, okay, so let's say A is water again. And say we have, I'm going to make this one a little bit more complicated. Well, say we have, we'll say with 500 grams of water again, at an initial temperature of 25 degrees Celsius. Okay, now B is going to be ice. Let's say we have 90 grams of ice. And that the initial temperature of the ice is minus 20 degrees Celsius. Okay, so again, this is where these pictures really come in handy, I think. Because, well, let's start drawing it. So we've got water here. I'm going to draw this a little bit smaller. Initially, system A, this is water at 25 degrees Celsius. And what's going to happen to this water? It's going to cool off to its equilibrium temperature. Now again, there's actually a bit of an assumption here that this is all that's going to happen. And I'm confident in this, even though I'm just making up this problem. Again, we have a lot of water, relatively small amount of ice. But if we had enough ice, what could happen is we could just freeze all of the water and end up with a solid block of ice. But right now, I'm going to assume that there's enough water that that's not going to happen. So I'm going to say A is just going to go from here to here. We'll call that Q1. Okay. Now, what about the ice? Now, the ice, we have a block of ice at minus 20 degrees Celsius. So again, this is solid. Now, the first thing that's going to happen, we'll call this Q2. Remember, if you heat up a solid, it's going to, you're going to cause a temperature change up until it gets to the melting point. So first we're going to heat up this ice until it gets to 0. But again, then we're going to keep on adding heat. So we'll call this Q3. And we're going to melt this ice. However, it's still not in equilibrium because now the ice is at 0 degrees Celsius. And so now we have to warm up this melted ice water until it reaches equilibrium. And it's very easy to neglect some of these parts of it if you don't actually draw out the entire process. So we've got this, I see this all the time, where you go from like minus 20 just in one step to the final temperature, and forget about all this stuff in the middle. I've seen students do that. But if you draw these pictures, yeah, you've got very cold ice. What happens when you add heat? Again, you're dumping this ice in warm water, so energy is going to flow into the ice. So we know that that's going to cause this temperature change up to 0. And then it's going to melt, but it's still going to be 0. And assuming that this didn't completely freeze, then we're going to go to this equilibrium state, equilibrium temperature here. So again, the basic idea, we have Q1 plus Q2 plus Q3 plus Q4 equals 0. So again, we're making this assumption that nothing is escaping into the environment. Not a perfectly valid assumption, but we're still keeping things simplified a bit. Now, I don't have room to write this whole equation, so what I can do is just write out Q1, Q2, Q3, and Q4. I'll write these terms out individually. So again, look what's going on with Q1. This is a temperature change. So we have C times mass of A times delta T, which would be TE minus 25 degrees Celsius. That's delta T. Now I'm going to write a W here, because we want to remind ourselves that we have two specific heats. So remember, specific heat, that only applies to temperature changes. When you have Q equals Cm delta T. But we have, here's a temperature change. We also have a temperature change for system B when it's in the ice state. So we have to distinguish which specific heat we're actually going to use in each of these processes. Okay, so that's Q1. Now again, to find Q2, well, here we are. This is a temperature change, so we're using this equation. But now we have the specific heat of ice. Now, delta T, we're going 0 minus negative 20, so that's just going to be 20 Celsius degrees. Now, Q3 is not a temperature change. We're at 0 degrees, we're ending at 0. This is a phase change, so we'd have MB times the latent heat of fusion. And finally, Q4, that's this temperature change. Now, this water is in a liquid state. So we use the specific heat for water times MB times TE. The temperature change is TE minus 0, so just TE. One final point. We always want to be careful with any equation that involves temperature. But as we discussed before, temperature changes can be either Celsius or Kelvin. It's the same number either way. So delta T, we don't have to convert things to Kelvin. We don't want to convert things. There's no reason for that at all. So now we add up all this and we get 0. And the biggest challenge is going to be just finding room on the board. So what I'm going to do is I'm going to calculate what I can, just numerically. So let's start out with this. Let's do CW times MA times 25 Celsius degrees. So what we're calculating is just this part here. We don't know what TE is, so we're distributing this. We have CW MA TE, and then minus CW MA times 25. We can calculate that part and get a number. So I'll do this and then write down the result. Specific heat of water is 4186 joules per kilogram Celsius degrees. Now the mass of A, this is 500 grams. Let's convert it to kilograms by dividing by 1,000. So basically, we have 1/2. Here, I'll leave it like that though. And then times 25. Actually, this will be easier. And we're just going to get a number in joules. The kilograms are going to cancel out. Celsius degrees are going to cancel out. Yeah, let's see what we can do with this number now. 25 times 5 is 125. And then 100 here. And then I can do like 4.2 or 4,200. We'll round off a little, divided by 1,000. So this isn't going to be too bad. Like we can calculate 125 times 4.2. And then multiply by 100 at the end. So this whole thing, I'll just do that. 525,000 joules. So I'm going to write this off to the side. So we have a CW MA times 25 Celsius degrees, 525,000 joules. So that's a pretty big number. Let me just double check that. 25 times 5, 125 times 100 for that. Yeah, I think I actually did make a mistake. Yeah, that number was a bit too big. I forgot it was 4.2. So it's going to be around 52,500. Because of that 0.2. Okay. So I believe that number, 52,500 joules. Now I did make a bit of an approximation. I rounded this off to like just 4,200, but otherwise we're good. Okay, so that's that piece. Now let's look at the next thing that we can calculate. Here we have CIMB times 20 degrees Celsius, or Celsius degrees. So yeah, we're just calculating the pieces we can. CIMB times 20 Celsius degrees. So again, we'll do it here and then just move it over. Okay, specific heat of ice is around 2,000 joules per kilogram Celsius degree. Mass of B is 90 grams. So that'd be 90 kilograms over 1,000. And then times 20. This is going to be a much simpler calculation. Again, kilograms cancel, Celsius degrees cancel. So 20 over 1,000 is just 2. So again, let's do 90 times 20. That's 1,800. Just doing that, and then times 2. So it'll be 3,600 joules. So a much smaller number for that term. Yeah, I believe that number is right. Okay. Now we can calculate Q3 as well. So that'd be MB times the latent heat of fusion. So we'll do that here. We have 90 grams, or 90 kilograms over 1,000. Then the latent heat of fusion, I'm going to look that up. That one was 33.5 times 10 to the 4th. And that would be joules per kilogram. So again, that's going to cancel. Okay, so what I'm going to do, I'm going to just a little carefully. I'm going to write this as 33.5 times 9. So here we have times 90. So I'm going to write this as 9 times 10. That'll be 10 to the 5th. And then divided by 10 to the 3rd. Okay. So that'll be the answer. So I'm just going to multiply this. 33.5 times 9. So it'll be 45, 31. So that's going to be around 301.5. And then times 100. So we've got 30150. So yeah, if we just multiply that by 100, 30150. And again, that would be in joules. Okay, so we're just calculating all these little pieces. And again, just the things that we can calculate. Remember, what we're doing, we're adding all this up and getting 0. So, Q1, we're going to have, I think I'm going to just try to write it out the long way now. We've got a lot of the pieces. There, we've got CW, MA, times TE. Actually, I'm not going to write this out yet. I want to leave this room. I'm going to calculate CW times MA. So I'll write this down here. CW times MA. And I also want to calculate CW times MB. So again, both of these are specific heat of water. So we have 4186 joules over kilogram Celsius degrees times 500 grams, so that'd be 500 kilograms over 1,000. So this fraction is going to be 1/2. So let's just do 4186 divided by 2. So it'd be 2,093 joules per Celsius degree. And then for CWMB, we're going to have 90 here. 90 grams, so that'd be 90 kilograms over 1,000. So I'm going to approximate this again. I'm going to take 90 times 4.2. So we're doing 4186 divided by 1,000. That's 4.186. Let's say 4.2 times 90. That would be joules per Celsius degree. Or we can just do 42 times 9. Let's do that. So this is, I'll just write this over here, 378. Okay. So, yeah, I just want to get as much of the numerical stuff out of the way as possible. And now let's write out this whole thing. So Q1, we have CW. I'm going to have to distribute this. MA times TE minus CW MA times 25 Celsius degrees plus CIMB times 20 Celsius degrees. You know what? I'm going to do this. Plus Q2 plus Q3. Just to shorten the writing here, because we know what these are. And then plus CW MB times TE. If we add that all up, we should get 0. Okay, so again, Q1, I broke it up into 2 terms. that and that. And then Q2 plus Q3, I just left those just to save room on the writing. And then Q4, we don't know what that is. And the reason I'm doing it this way is let's combine these two terms that have TE. So we have TE times CW MA plus CWMB. So that covers these two terms. And then let's move all the other stuff to the other side. So we have CW MA times 25 Celsius degrees minus Q2 minus Q3. So now we're almost done because we know this right side. Actually, I'm going to do this a little differently. I'm going to write it minus Q2 plus Q3. So we can just add up these two things and compare it to this and subtract. And we also know this part in parentheses, that's just the sum of these two pieces. So TE, let's figure out the right side first. So let's add Q2 and Q3. Q2, that's this one, and Q3 is this one. So we have 30,150 plus 3,600. So we have 33,750 here. That is in joules. This term here is the top one. This is 52,500 joules. So now we can subtract these, and this is just a number. See, 52,500 minus 33,750. Let's subtract. Getting 18,450 on the right side. So that's 18,450 joules. Now we have to divide it by the bottom, which is just the sum of these two terms. So we have 2,093 plus 378. Okay, so let me just check. That was a 7. Okay, so this would be 2,471 joules per Celsius degree. So now I want to round off a little bit. This is around 18,450 divided by, say, 2,000. Let's just say 2,500. So if we take 1,000 off, this is, let's say 18.5 divided by 2.5. So again, a bit of a rounding off here. 2.5, that's 5 halves. So let's see, that'll be around 37 divided by 5, which is around 7 degrees. So that's 7.4 Celsius degrees. So again, I did some rounding off, but I did want to get a number here just to check and make sure that everything actually worked out. Because if we had enough ice, actually it wouldn't even take too much more ice, we would have just wound up freezing everything and end up with a big chunk of ice at the end. because the ice started out very cold, so we had to, a lot of it went into just like completely melting it. That took a significant amount of energy to melt the ice. It was 30,150 joules. And so if we added enough ice, all the energy that goes into melting the ice, it's coming from here and cooling it off. So if we had enough ice, we would cool this temperature down to 0 and end up with just a big block of ice. So I wanted to go through all the way to the end and just make sure that our answer made sense. And around 7.4 degrees Celsius. And again, that's a bit of an approximation, because I don't have a calculator, but fairly confident it's not too far off from that number. All right. I think that's a good point to stop. There's another example, but I don't know how I could possibly fit it on this board. So that's an example in the notes. So maybe I'll do that like live in class or something. But as far as we're concerned, the only difference in this next problem is that we have a container which we're also taking into account. Maybe what I'll do is I'll outline it but not go through all the steps. That way you can just look in the notes and it's worked out in there. So I'm going to erase all this. I'll read the problem and just describe the procedure but not go through all of the steps. So I think that'll be a good place to stop, because that's in the notes and we won't have to go over it anymore unless there's any actual questions. Now again, in this problem we're still going to make this assumption, which is not entirely accurate. We're going to make this assumption that nothing is going to escape in the environment. So let me read the problem. All right, a 7-kilogram glass bowl, where we're given the specific heat of the glass, which is 840 joules per kilogram Celsius degree, contains 16 kilograms of punch at 25 degrees Celsius. 2.5 kilograms of ice are added to the punch. The ice has an initial temperature of minus 20 degrees Celsius. The ice is, as far as heat capacity, just water, 4186. We're assuming that there's nothing between nothing escaping into the environment or escaping in from the environment. And then what is the final temperature when equilibrium is reached? So here we've got, we have three things in our system. We have our bowl. So again, I'm not going to include all the numbers here. I'll just write out bowl, which was at 25 degrees Celsius. We had the punch, which was in a liquid state. And the punch was also at 25 degrees Celsius. So these two were in equilibrium with each other. You have a bowl and punch, they're going to be in the same temperature. Like if one of them was warmer, heat would flow. But then we had ice, which I'm actually going to write it as water. But it's in solid form. This is minus 20 degrees Celsius. And so now everything is going to come into equilibrium. So what's going to happen to the bowl? It's going to cool off. That's it. It's already a solid. Nothing else can happen here. So we're going to have a bowl at some equilibrium temperature. We'll call that Q1. Now again, we do have this issue where the punch could completely freeze solid, but it's even stated in the problem that's not going to happen. So the punch is going to remain a liquid at some final temperature TE. That'll be Q2. Now the water is going to go through all these steps we had before. Well, first it's ice. It's going to heat up to 0 degrees Celsius. That would be Q3. Then it's going to melt, which would be Q4. So once it melts, it's still at 0, and then we have to heat it up. Oh wait, sorry, it melted, so now we have water. Liquid water at 0 degrees Celsius, but then it has to reach equilibrium temperature, TE, so that would be Q5, and just like before, just add it up. Q1 plus Q2 plus Q3 plus Q4 plus Q5 equals 0. So again, I'm not going to even write down any more on this, but we'll talk about each of these terms. So Q1, this is a temperature change, where we'd have the specific heat of the bowl, which was given, times the mass of the bowl times TE minus 25. Q2 is a temperature change. So again, this is just water basically, 4186 times the mass of the punch times the temperature change, which is TE minus 25. And then Q3 is a temperature change, where again, this is ice. So it's a solid form of water. So the C you would use here is 2,000 joules per kilogram Celsius degree. So you got to keep those things straight. And the temperature change is 20 Celsius degrees. We already know what that is. Q4 is a phase change. You want to use the latent heat of fusion of water times the mass of water. And again, these two things you can calculate as numbers right away. Because there's no unknowns. The only unknown is TE. So again, these two terms and this one, Q5, we also don't know what that is. But it's a temperature change. This would be specific heat of liquid water, which is 4186, times the mass of water times the temperature change. And again, all the details are in the notes. I don't have room on the board. But again, once you see it set up, it's kind of just an algebra problem at this point. So again, when doing these problems, I highly recommend drawing pictures like this. And that way you're going to see everything that's going on. And yeah, and then also being careful that you put in the right specific heat for each case, or for phase changes you use the right latent heat. You never have to memorize those things. Those are in the equation sheet. So yeah, you don't have to memorize those numbers, but just make sure you use the right ones. And then there's a lot of calculations involved. So in the end, we know we've got to get a number that's going to be between 0 and 25 degrees Celsius, once we do all the calculations. So again, it's very easy to make mistakes in these little things, so just do it slowly and carefully, and check your answer at the end to make sure that it makes sense. Just, again, if you do all the steps, it turns out to be around 10.6 degrees Celsius, which is what we said it had to be, between 0 and 25. Now, 0 would be a possible answer if we added enough ice. Everything would just freeze solid. And then we wouldn't even have Q5 at all. But we're told in the problem that's not going to happen. So like the warmest thing to start out was 25 degrees Celsius. So the final answer